So this one is the first example, and the first example is how to be able, I have a GPU, I want to get some information on the GPUs, I want to know how many of them, what is the name, what is the vendor. Sometimes you may want to get, if you have a PCIe number or something like that, you want to go see the information. And here is just to show you that it is really C++, right? SYCL is really C++, so you can use all your auto if you want, some function C-Cloud platform, return you std vector, so you can iterate over it. Then get info, because it's C++. In C++, we like overloading for a reason that I ignore. But so in get info, you don't take a parameter, you overload to the type you want. So if you're really good at SYCL, you can at C++, you can ask yourself, how can I read those things as a command line argument and after use it as a template argument? It's highly non-trivial, but you can do this kind of thing. So this one is ready to show you that everything is C++. And if you like C++, you will like SYCL. If you hate C++, SYCL is maybe not the best fit for you. So what you want to do is just iterate over the platform. For example, you may have some people have a desktop, where they have GPU with both Intel, AMD, and NVIDIA in the same box. So they will have 3 platforms, and each platform will have a particular devices. So you can do that if you want. In this case, because I am the frontal node, I will see only 1 GPUs and 1 platform. And so let's see, 0, I don't see any is too far. Yeah, so you see here we saw that we have 1 platform, and it's the NVIDIA CUDA backend NVIDIA. If you run on Intel, it will be level 0 backend, for example. Some people ask, you may have OpenCL, OpenMP, whatever they want to do. And inside, we have also this device. All versions of SYCL were required to provide you a backup host, like in OpenMP. In OpenMP, if you don't have an OpenMP compiler, they should run on the host. Same in SYCL. If you don't have any devices, you should be able to run serially. So this is what they call the host platform. And the host platform is, of course, have a 1 device with not a GPUs. So this is it. So it was just to show you C++. Now let's do something that may be more useful. Let's try to submit a kernel, your first kernel. My first kernel.cpp. And this one is ready to show you the beauty of C++ with double nested lambdas and all of these kind of things. So at the beginning, it have been scary. I was doing Fortran before, so I don't know this kind of strange character and this kind of thing. So at the beginning, you just copy-paste it, and after 100 copy-paste, you say, OK, I will sit down and try to understand. And so what you want, a lambda is just an anonymous function, and so you can use something inside from the lambda from outside the lambda. And you need to understand, like we discussed from the Cocos people, if you need to make a copy or just a reference of it. So here, some people also say, can I use any STL inside device function? The answer is no, right? GPU are really stupid things. They cannot allocate memory. They cannot do a lot of things. So you cannot use a lot of functions. For example, you cannot use stdcout. I'm not sure if it even works in Cocos or something like that, because stdcout is kind of hard if you think about it. So what you do, you can create a single stream. So here so printf works, but not stdcout. But you can here we'll create a SYCL stream. So it is inside the queue.submit, but it is not inside the submission. So this one is just a scope to say we are not yet in device code, but we will do something in device code. So from the queue, you will submit something. You create a stream. And after here, a single task is really something you want to execute only once. So not a parallel for, not nothing, just once. So it's really nice for testing. For non-testing is kind of strange. Not so many people use single task. And here I just print hello world. And after I close all my scope, I need to wait, like Abby said, because if you don't wait, you have a race condition. Your program may finish before your kernel finish, who is just, we don't care, but it's cleaner to wait. Maybe a difference as cocos, we don't have any init, we don't have any finalize, so you don't have this problem. And you need to create a queues here. So you see, here we create a queue with a default selector. So if you want to run an FPGA, you will put FPGA selector. If you don't put nothing, the runtime will choose for you. So most of the time they will use the GPU. And if you don't have any GPU, it will use the CPU. But here we are explicit. So let's see if this thing works. The beauty of live demo. Huh? So here, indeed, perfect. So we show that we run on NVIDIA, and it printed a word, what we expect. So this is nice, but now we want to run maybe more than one item, maybe more than a parallel for example. So 2 parallel 4.cpp. And here, the only thing we'll change, we'll still create a stream, we'll create all of this. But here now, we replace the single task with a parallel 4. And here I put the OpenMP code for the people who do OpenMP, who are more familiar with OpenMP. So ch parallel 4, and after I pass a global range. And after in this global range, I will get my index. So my index is something I can use to know where I am in this iteration space. And here I will just print this iteration space. So for example, in OpenMP, it is your index, right? You loop over the index, and after you print the index, here you do a global parallel global range. So please note two things, like in OpenMP, the order in which I will get the index is totally undefined, right? Because parallel 4 can execute it in any order. And in a stream, here I put some variable, and here is the size of the stream. So if I start printing too much, I will override my stream. So you may have some issue. And here, you see I do something tricky. I don't use queue.wait. I just do .wait at the end of the queue submit. It is because, and we can see it later, we have by default out of order. So how can we synchronize between all these different kernels? In OpenCL, and it comes from OpenCL land, and it comes also from all the tasks. If you do any tasking, it works also the same. Every time you submit a kernel, you can get an event. And from this event, you can do a lot of things. You can, for example, wait for this event to finish. If this event finishes, the kernel finished. And you can use also this event to make some dependencies. So you can say, I have this event, and I will submit this kernel only when this event finished. And in this case, this is what we are doing. We are not waiting on the queue to finish. So waiting on the queue means I want all the kernel in the queue to finish. We are just waiting on this particular kernel to finish. So the difference between queue.submit.wait and queue.wait is really the granularity. Here we are waiting only for this submission, where in queue.wait we are waiting for all the submission inside. So I think I already compiled it. Perfect, and I think I have some G10. Yeah, doesn't seem to work. Yeah? No, okay. Oh yeah, 2, exactly, thank you very much. Oh, perfect. So 0 and G5, for example. Exactly 5, and I think if you, and you see here, I rerun trace, should be in the same order, but if I start being bigger, then 226 should be the same, maybe. So sometimes it should be, you cannot rely on this thing, it depends how they run or if they serialize, if they single thing, but here we are lucky. I mean lucky. We run in order, but you see here, for example, if I put 45, the orders start to be totally different. We have 32, 0. So it's just to show you that it is totally deterministic. So just need to be, doesn't never rely on the order execution. So we did some progress. Now we know how to submit parallel 4. You know, it's just this kind of double lambda. So one lambda for the compute group handler and the lambda after just to ready to the submit. And I think now the third one is maybe the first thing we teach you if you did some CUDA programming and everything is one the way of getting good performance is you tuning your local workgroup size or your WAP size. I don't know it's called in CUDA. Abby can correct me. But it's to tune how many threads you want to spawn and everything. So you go, and in SYCL we have the same thing, same in Cocos, I'm pretty sure. So it's not a range, and we go from a range to an ND range. And in the ND range, you say this global range, and after you say also the size of the local range. So you don't say the number of, in OpenMP, it's like you have the number of team and the number of threads. You can play with OpenMP num team and OpenMP num thread. We can do the same here. And by tuning those parameters, you can really gain huge performance boost. So this is the standard optimization when you write some kernel. It is to tune those parameters. We got some question, and I think we discussed a little bit in Cocos. What are the best value for those? My answer is we don't know. It's just auto-tune. Just run a lot of benchmark and just take the best. Honestly, it's really, really hard to get some feeling of which one will be the best because it depends on a lot of parameters. And you see here, I create an ND range of 1 dimension. You can have up to three-dimensional ND range. But here you create only an ND range of 1. I create a range, global range, local range. And after, because I use this ND range, I can have access of a lot of introspection, like in which global size, in which work threads, warp, or all this kind of information. So in SYCL and in OpenCL, we can read global ID with really the index as before. So get global ID, so get global range with the maximum system, and local ID, yeah, local range and everything. So we'll not go in through detail because it's just totally obvious. You just read, you open the spec and you see what they are doing. But it's just to give you an idea that you have some introspection capabilities inside this iteration space. If you do more fancy algorithms that we show with Abby, where you have some synchronization between the warp, between the subgroup or this kind of thing, you can use those things to get. So maybe the difference, I think in CUDA, and it was a problem, I think, when people port large code base from CUDA. Here, it's not a free function, right? In CUDA, it is a free function when to get the thread ID, where here you need this index. So if you start porting your code and you have multiple function call, you need to add a new parameter because we don't rely on global variable and magic function. We got some free function, we read some state, we just pass an object, and you need to pass this object. So it was a little painful for some people to refactor their code to be able to pass this index if you have a lot of function. Let's see. Don't hesitate if you have any question. But so with submit kernel, I heard that some of the time we need some memory. I don't know why. Memory is painful, it's slow, you should not use that, but sometimes we need some memory. So we'll go over a little example that Abby shows, the first one for buffer. I really like buffer personally. I think buffer is the evolution of the programming language, right? Before it was C. In C, we were like, okay, I will malloc and free my memory, I am smart. And after we realize we are not smart, we cannot do that. So C++, everything is automatic, garbage collection. But we are like, it's okay, for GPU, I will do the data transfer myself, I'm smart, I will do when I do the copy from the CPU, the copy to the CPU. I know when I will need my synchronization. We are not, it's really hard. So in SYCL, we have buffer, and buffer does everything for you. So buffer has really a descriptive way of saying things. So you create buffer with a little bit like SYCL, Cocos view, where non-owning data, and you just use buffer, and after accessor to say buffer to say if you want to read data, write data. And for example, the runtime can do some optimization, because if you write only to a buffer, so we have something called discard write, that means you don't need to allocate it on the CPU. You don't need to do a data transfer from the CPU to the GPU because you will write to it. So you can just directly allocate it on the GPU and no need to do a data transfer. Same if you have multiple write, you can just do it in parallel. You don't care, or you can duplicate. So you have a lot of different optimizations that you can do. And the runtime is free to do it because you tell him what you will do with this buffer. Because of aliasing rule and everything, the compiler cannot do that for you. So you need to help the compiler by giving some information. So here, I think we just initialize some data on the GPU. So we create a buffer. So we create first a vector. So from this vector is really, we can do a malloc, we can do a lot of things. It's just some memory that we have on the GPU. Then we create a buffer with no knowing of this thing, so it's just a view to talk like a Cocos. So we create a view of this buffer. And then inside our kernel, we'll not use directly this buffer, we use some accessor. So the accessor is ready to describe how we will access this buffer. So here, for example, I say that I want to write only, and I can put this no init to say, oh, trust me, I will write on it, and you don't need to do any initialization of this buffer. So I do that. Then on my other lambdas, I capture by values this little accessor, and I can initialize this accessor. And after at the end, you see, I don't need any wait, because you have this implicit rule that at the buffer destruction, they will wait for everybody. So you don't need to care if the buffer go out of scope. Yes?
On the accessor, where is the magic that tells whether the queue is a queue on the device or on the host? Makes it it's going to be accessible. Where does it happen?
So here, the command group handler here is creating inside only this queue. So from the command group handler, you know in which queue you are. This is why you need a command group handler, is to do the thing. And you will so here we write only on the accessor. The accessor is linked to the buffer, and the buffer was created on A. So when the buffer will go out of scope here, a lot of things will happen. Synchronization, the buffer will destroy, so they will copy the values of the GPU memory back to the vector, and now we can access the vector here with some nothing. So it's really, really powerful, maybe a little verbose. You see we need to have a lot of different things, but it really gives you a lot of free of mind because you get all the information to the runtime, and now you just need to trust the runtime, but it's purely mechanical for him. It's really easy to use. So let me try to compile this thing. Make for buffer. Buffer. Oh, perfect. Then I just run it. G10. And you see, yeah, not really impressive. So if you don't trust me, you should not trust me. You should profile this code. If you profile this code, you will see using NVProf or whatever your favorite profiler, you will see only one data transfer. You will be a data transfer to the host, to the GPU, to the CPU. You will not see a data transfer from the CPU to the GPU. If you see a data transfer, it's a bug. Two data transfer, it's a bug, and you should definitely report it. I'm not a permuter guy, so I don't care that much about NVIDIA, but on an Intel, I'm sure that we don't have any data transfer. So this is the verbose kind of a thing. I can show you quickly how can you do the same with USM. So set buffer.usm. And it will be the same code where here we think we are smarter than any runtime. We know what to do. So I just use a malloc shared. So malloc shared, as Abby said before, is really this kind of thing where it is a memory. And I think in Cocos we think it's a memory which is accessible in both the CPU and the GPUs. And depending on the hardware, you will have some page migration if you try to go from one to the other. So it's really nice. The code is really more terse. And so you see, I create this single malloc shared. You see C++, so I don't need to do size of int and some static cast. I just overload my little malloc shared. I pass a queues. So you see here, little tips. This malloc shared return you a pointer. It doesn't return you an event. So that means this guy is blocking. We don't use the queue to submit an allocation. We just hit the queue to know in which device we need to run. So this thing is blocking. Then I have my memory, and then in my parallel for, you see here I can do directly q.parallel_for. I didn't do q.submit, and after I got this command group handler and command group handler dot parallel_for. It's because I don't need the command group handler. So we have this shortcut notation that if you don't need the command group handler, you can just remove it. Yeah.
When you said it's only blocking block Q, right?
So this, I was wanted to share that the allocation is blocking. It's not, it makes sense, right? I mean, it's maybe obvious.
Semantic, but you could implement it this way, but the semantic isn't it that it's only meant to block on Q?
So the parallel_for is asynchronous. So this is why I need to do wait. The memory allocation is always blocking. We don't have anything. The queue is just a shorthand to get a context and a device. We don't submit anything. So malloc.
Does it mean that if later there is some support for allocating on the stream, you guys are...
Yeah, we need to change with a new parameter to say... Yeah, by the way, yeah, we didn't see. Nobody did that yet, so we are safe. But if one day a vendor does that, it's over. So you see here, it's really, really terse. So it's a nice slide we like to show if we want to be proud. Okay, it's nice, but now it relies on a lot of you to do the correct thing and to do the synchronization. But indeed, it takes less character. And in fact, if you want to do a little golfing, you can just put some auto here. So you save a few characters. No, it's really nice. Yeah, and one can argue that this thing is maybe not the best performance thing, because so what will happen is here it will allocate on the CPU. Here we'll do a lot of page fault to go back on the GPUs. And here at the end we read back on the CPU. So we have page fault again to read from the GPU to the CPU. So a lot of implicit stuff are going, but it is working. And it is really maybe the most natural step when you port your code, because it's kind of super easy. Oh yeah, and you see here, as we say before, we capture by value and not by reference, because if you capture by reference, your pointer will be garbage. Okay, so I think we are only 2 minutes, and I think I finished my example. So maybe the last one I can show you. Let's see what can I show you. I can show you maybe the events or some fancy stuff that doesn't compile, because let's see if I have something. Yeah, maybe. Just a code to show you that you can do more fancy thing. Just for the last 2 minutes. So I think I stole this code, maybe it's from Intel. And I think it is some MKL, is to show you that you can use MKL, one MKL that Abby discussed. And so you can use it, and it is really nice, even if you don't want to use, you're like, I prefer OpenMP, I prefer Cocos or whatever. Using SYCL just because now you have access to this portable MKL is really nice. I don't want to say how many project I see where the layer of abstraction was just to be able to call cuBLAS or eBLAS or MKL. It's just painful. At least here you can just use one MKL, and one MKL will just leave a thin layer around cuBLAS or MKL if you're on CPU. So I think this one was not the most complicated. So let me, I think it was the one with the matrix mul MKL inter. I think, I don't remember. But it's okay. So it's just to show you that you have a lot of way also to do some synchronization inside the local group. You have hierarchical parallelism too. You have a lot of things. So here I just tease you with simple code, but you can do really more advanced code. And I think, perfect, we're on time, that's it. So yeah, don't hesitate to run the example. Everything should run fine. And use any tools or something like that. And don't hesitate. So now on next speaker will be another way of seeing this problem. It will be Rajas. And Rajas is another, the third big of the programming model to target GPU with C++. And we'll have a talk about this. And I'm excited because I don't know that much about Rajas. So. Yeah. Thank you.